Hello everyone, and welcome to some more remote learning. Today I'm going to go further with parametric equations, and we're going to get into taking the derivative. But before we go over this new Calc 2 concept, I want to go over a little bit of a review of parametric equations, really working on understanding this concept because it will come up in later courses. So the first review problem, we're going to draw the parametric curve x equals 2 cosine of t and y equals 3 sine of t squared for 0 is less than or equal to t, which is less than or equal to pi, by eliminating that parameter. Now remember, when dealing with sine and cosine, we want to use that nice Pythagorean identity, that the cosine squared of theta plus sine squared of that same value is equal to 1. So we're going to manipulate our parametric equations to get that identity. Now note this is a little different than each of the examples in the last worksheet because cosine is raised to the first, but sine is already squared. So let's first solve for that cosine and square it. So we'll have x over 2 if we divide both sides by 2, and that'll give us cosine of t. Then we'll square both sides to get that cosine squared. So now we have something we can plug in for that first part of our identity. Now when we look at y, if we divide by 3, y over 3, well, that is equal to sine squared of t. So we don't need to worry about squaring both sides of this because we already have that squared. So y over 3 is going to go in for sine squared of that theta. So we're going to have x squared over 4 plus y over 3 equals 1. Now I'm not quite sure what this looks like, but I can solve for y and simplify. So if I subtract x squared over 4, I'll get y over 3 equals 1 minus x squared over 4, and then I'll multiply both sides by 3 to get that y is equal to, distributing that 3 minus 3/4 x squared. So I know I have a parabola where my y-intercept is at 3 and that parabola opens down. However, I'm restricting my t values. So when t equals 0, what is x? Well, when t equals 0, the cosine of 0 was 1. So when t equals 0, that represents x equaling 2. And when t equals pi, if I was to plug pi in for the cosine of t, cosine of pi is a -1. So that represents -2. And I have my x values in between that. So when I'm drawing this parabola, I want to start at an x value of -2 and end at an x value of a +2. Note, however, that when I'm plotting, I'm starting with my positive values and working my way to the negative values. So if we think about traveling along that parabola, we're going to be moving towards the left. So here's x, y, and x of 0 is contained within this interval, so I'm going to plot 0, 3 on my graph. And then I want to go to -2 in the x and a +2 in the x. But remember, again, I'm starting at those positive values, so the positive orientation or the direction of my parametric equation is starting towards those positives and going towards the negatives, which I'll draw arrows on my graph once I get it plotted. So plugging 2 in for x or plugging -2 in for x, because we're squaring that value, we're going to get the same exact number. -2 squared is 4 and 2 squared is 4. So when we have 3 minus 3 times 4 over 4, my 4's will cancel out, so that'll be 3 minus 3, which equals 0. So when I'm at -2 in the x or 2 in the x, I'm at 0. So I'll draw my parabola and labeling that direction with arrows. So that's my parametric curve in part 1. We use that identity when dealing with sine and cosine to help us get our equation, making sure to take those bounds into account and also the direction. So number 2, it says give parametric equations that describe a circle with a radius of 3 centered at the point 1, -2 with positive orientation in the clockwise direction. This is where we're going to reference that general parametric equation form for a circle. So if you remember that equation, feel free to refer back to your notes. That parametric equation is x equals x naught plus a cosine of bt, and y equals y naught plus a sine of bt. That's the general form for our parametric circle, where a is our radius. So I'm just going to fill this in as I go along. If a is our radius, then I'm going to have 3 sine of something t, and x is also going to be 3 cosine of something t. Next, I'm going to take my center into account. That's my x naught, y naught, just as my radius is a. So x naught, plugging that in, I'll have 1 plus 3 cosine of something, don't know what that is yet. And then for y naught, that'll be negative 2 plus 3 sine of, again, I don't know what I'm plugging in yet, but this is the positive orientation goes in the clockwise direction. So remember, B dictates whether we're going clockwise or counterclockwise. If we have a negative B, we're going clockwise. If we have a positive B, we're going counterclockwise. So I'm going to make B negative 1. So I'll just plug in negative t. Now we want to describe a circle, and we want to describe that full circle. So because I use the b of negative 1t, I need to set my bounds as starting at 0 and going all the way around to 2 pi. If I set b as negative 2, look how my bounds would change. If I put a negative 2t in, then my bounds would be from 0 to pi. So you can see that there's essentially infinitely many options for how to write these general parametric equations. And that's because we're choosing what t is. Either way of writing that gets a full circle. I'll just do negative t as the input into both cosine and sine. So that we're going from 0 is less than or equal to t, which is less than or equal to 2 pi, to get that full circle. So those are the parametric equations that describe a circle with a radius of 3, centered at the point 1, negative 2, with positive orientation in the clockwise direction. In number 3, we're going to give a geometric description of a curve described by the parametric equations x equals 4 cosine of t and y equals 2 sine of t for 0 is less than or equal to t, which is less than or equal to 2. And we're going to be sure to include the direction of positive orientation. Now, right off the bat from this, we'll be able to decide where our center is, because there's no shift, there's no adding or subtracting from that sine or cosine. So our center is going to be at the point 0, 0. We also know we're going to be starting and stopping at the same point because we're multiplying t by a positive 1, and we're going from 0 to 2 pi. So we're going to start at the same point and go all the way back around to that point again, and we're going to be going counterclockwise. So our direction is counterclockwise. What's our radius? Well, radius is usually a, but look at this problem. We have a 4 and we have a 2. Those aren't the same at all. So this isn't actually a circle. It's called an ellipse. We're going to have an oval. So you can still think of the terms multiplied to sine and cosine as essentially a radius, except now that's going to change. So along our x-axis, we have a radius of 4, which means that length along that axis is going to be a total of 8. And for y, we have a radius of 2. So you can see how this is going to be an oval where we have a longer distance between my points on my x-axis and a shorter distance between those points on the y-axis, because you can think of that, essentially the radius, as 2 on that y-axis. So that length is 4, whereas in the x, my length between my points is 8. The longer distance that occurs is considered our major axis, and that distance again is 8, whereas for y, that's going to be our minor axis, where the distance is 4. So if we can envision this quickly, we would have something that looks like this. Here would be the point 4, 0. Here would be negative 4, 0. Then we would have 0, 2, and 0, negative 2. So you see that we get an ellipse. Here, my distance along my major axis going from negative 4 to positive 4 is a distance of 8, and along that minor axis going from negative 2 to 2, I get a distance of 4. So how we would describe this geometrically would be, we would describe the shape, so it's an ellipse, centered at, where is it centered at? 0, 0, with a major axis length of 8 on the x-axis. So saying descriptively that our major axis is our x-axis, which is 8, and a minor axis, which occurs on the y-axis, that length is 4. And we also have to say the direction. So it's going to be generated, and what was that direction again? Counterclockwise, because that B is positive. So again, it's an ellipse centered at 0, 0 with a major axis length of 8 on the x-axis and a minor axis length of 4 on the y-axis, generated counterclockwise. So our last quick review example, we're going to consider the parametric equations a equals 2 plus 3t and y equals 5 minus 3t, which describe a line. And because it's a line, not a line segment, our t goes from negative infinity to infinity. So we're going to find the slope, and we're going to find a point on the line. Now, if you remember that general parametric form for a line, slope and the point are super easy to figure out because we have x equals x naught plus a of t and y equals y naught plus b of t, where x naught, y naught is that point on the line, and b over a is equal to the slope. So right away, the point on the line is 2, 5, x naught, y naught, and my slope is b, negative 3, over a, which is a positive 3. Negative 3 over 3 gives me a negative 1. There's my slope, and there's my point. If you don't remember this general form of the line, that's okay. You're just going to have to do some extra work, and that would be by eliminating the parameter. So let's do that quickly just as a review. We're going to solve for t, so that becomes x minus 2 over 3 equals t. And all we need to do is plug that t value in to our y equation. So y equals 5 minus x minus 2 over 3, and that's all multiplied by 3. So 3 times x minus 2 over 3. Note, my 3's cancel out, so I'll have y equals 5 minus x minus 2. So this is pretty close to point slope form. If I subtract that 5 over, here I'll get y minus y naught equals m times x minus x naught. So you can see there's my 2, 5, and my negative 1 for my slope. Now let's move on to some new stuff. Now we're going to learn how to take the derivatives of parametric equations. So the derivative of a parametric curve, dy dx, well, if y is a function of t and x is a function of t, we're going to take the derivative of y with respect to t and divide that by the derivative of x with respect to t. Because you can see how this dd, essentially you can think of as canceling out to leave us with just dy dx. So knowing that, let's evaluate the following. We're going to find dy dx at t equals 3 for x equals t squared plus 4 and y equals 8t minus 1. So what I'm going to do first is I'm going to find dx dt, which we're going to take the derivative of x with respect to t. So taking that derivative of x, that's just our dx dt, with respect to t of this, however, t squared plus 4, that's 2t. Now I'll find dy dt. So that's taking the derivative of y with respect to t, which gives us dy dt, and taking the derivative with respect to t of 8t minus 1 is 8. So remember, dy dx is dy dt over dx dt. So I have that dy dx is going to be dy dt, which is 8, over dx dt, which is 2t. And remember, I'm solving for when t equals 3, so all I have to do is plug in 3 for t. 8 over 2 times 3, that's going to be 8/6, which simplifies down if we divide both by 2 to 4/3. So that's my derivative of y with respect to x for part A. For part B, we're going to find the value or values of t when dy dx is 0 and when it's undefined. And that's for x equals 2 cosine of 2t and y equals sine of 2t, where 0 is less than or equal to t, which is less than or equal to pi. Now, before we jump into this, I think it might be helpful to visualize what exactly we have. So doing a quick sketch, drawing this out, we're going to have an ellipse. We're going all the way around that ellipse because we're starting at 0 for t and going to pi, but 2 is multiplied to t. So we're going to wind up going all the way around. Our major axis is going to be x, and that radius is 2, so that major axis is going to have a length of 4. So I'm going to have the point 2, 0 and -2, 0. And for y, that radius is simply 1, so I have a length of 2 for my minor axis. So this will be a +1 and a -1. So you can see that if I was to draw this ellipse, I know that that direction is counterclockwise, which isn't too critical for this problem because I didn't specify that I wanted the direction, but let's just be thorough. So if we have 2 cosine of 2t and y equals sine of 2t, just looking at this picture, where would you expect your derivative to be 0? That's at a horizontal tangent line. So if you can envision, we would have a horizontal tangent line here and a horizontal tangent line there. So at 0, 1 and 0, -1, that's when our derivative's going to be equal to 0. So let's double check that. dx dt is, well, what's the derivative of 2 cosine of 2t? Remembering the chain rule, that's going to be -4 sine of 2t. And dy dt is equal to, derivative of sine of 2t is going to be 2 cosine of 2t. So dy dx is going to be 2 cosine of 2t all over -4 sine of 2t. So remember, our first step is we're finding when that derivative is equal to 0. Well, that's going to be equal to 0 when our numerator equals 0. So when does the 2 cosine of 2t equal 0? Well, 2 is never going to be equal to 0, so that's when the cosine of 2t equals 0, which the cosine of 2t equals 0 is going to occur at t equals, well, the first one's going to be pi over 4, because 2 times pi over 4 is going to be pi over 2. And the cosine of pi over 2 is 0. And that next one is going to be at 3 pi over 4, because remember, we're sticking between the bounds of 0 and pi, and 3 pi over 4 times 2, that's going to be 6 pi over 4, which is 3 pi over 2, which again, the cosine of that is 0. So those are my 2t values when my derivative is equal to 0. So I'll make a note that this is for dy dx equals 0, which we can see occurs here and here. If this period around was starting at a t value of 0 all the way around to a t value of pi. Now I have to think about, when is my derivative undefined? Well, as opposed to having a horizontal tangent line, that's when our derivative is 0. A vertical tangent line is when our derivative is undefined. So a vertical tangent line will be at those 2 points, -2, 0, and 2, 0. But what are those t values? That's going to be when -4 sine of 2t is equal to 0, which occurs when sine of 2t equals 0, which the t values for that are, well, one of those is going to be when t is equal to 0, because the sine of 2 times 0 is the sine of 0, which is 0. The next time our derivative is undefined, when that denominator equals 0, is going to be at pi over 2, because pi over 2 times 2 will give us the sine of pi, which again is 0. And then lastly, that end bound of pi, because the sine of 2 pi is also 0. So you can see that I have 3 different t values for that. Because we're starting and stopping at this point here, I am there twice on my graph. So I need to take into account both t values, even though it only represents one xy value. And this is for when dy dx is undefined. And again, that's when our denominator within our derivative equals 0, gives us something that's undefined. And just to help you, if you refer back to this when doing other example problems, I'll write out those xy values as well. So our derivative is 0 when x is 0, so that's 0, 1, and 0, -1. And our derivative is undefined when y is 0, which is 2, 0, and -2, 0. However, our instructions asks for the t values, so that's all that's necessary. And that's how to do derivatives of parametric equations. If you have any questions, please feel free to leave them in the comments below, and I'll answer them as soon as I can. So, good luck with your online learning, and see you next video.